Let's take a look at the Rankine cycle in a little more detail. We'll do some Rankine cycle calculations, do an irreversibility analysis of an example problem, and we'll look at scale up to find the mass flows that we need for running our Rankine cycle to produce a given amount of power. Here's our example. We have QH, heat coming in at a temperature from a heat reservoir at a temperature of 800 degrees C. We're ejecting that heat to cooling water, which enters at 25 degrees C. And when we specify this, we're going to try and produce 150 megawatts of power. So we have a pump, pumps the liquid up to high pressure. We have a boiler, superheater, that gives us a nice high pressure superheated steam that will go into the turbine, drop through the turbine, and to a low pressure that will give us mostly vapor, maybe a small amount of liquid allowed. We don't want to have much liquid as we go through the turbine forming, or that could damage the turbine. And we'll condense the steam using river water or cooling water of some kind to produce liquid again and put it back into the pump, raise the pressure, and cycle on through. So there's the example we're going to use, 800 degrees C, our high temperature, for our example problem. Let's take some assumptions that we'll have. We'll assume there's saturated liquid leaving the condenser. Ordinarily, you'll want to subcool that a little bit, but for this example, we'll take saturated liquid leaving the condenser. We'll have no pressure drop on our heat exchangers. Assume there's no pressure drop or negligible, and no heat loss from any unit. All of the equipment reasonably well insulated. So here's the data that we'll start with. Suppose we have a pressure of 1 bar, and 1 bar is equal to 100 kPa. And we'll raise it to our high side pressure through the pump to 100 bars, and go through our boiler and superheater, enter our turbine with 100 bars, and assume we have a temperature, high temperature of the steam, of 640 degrees centigrade. And that'll be the data that we have. What I've done is taken and indicated some of the initial findings from the steam tables based on this saturated liquid coming into the pump, quality of 0 at 1 bar, and a superheated vapor at 640 degrees C and 100 kPa, 100 bars going into the turbine. So there's our properties and there's our process. And let's start doing the analysis. First of all, we have our pump. And the work for a pump, you recall, the ideal work for a pump is the volume. This is work per pound, work per mass is the specific volume times delta P of the pump. That's the ideal work for the pump. Comes out to, when we put in unit conversions, we have a work of 10.3 kilojoules per kilogram. Continuing on with the pump, if we calculate the real work, remember when you're calculating work that you're doing, the real work always has to be more. So we'll divide by the efficiency of the pump. If we take a pump efficiency to be, say 75%, then our real work will be slightly higher, or 13.7 kilojoules per kilogram. Now, after we've calculated the real work for the pump, we can plug it back into the energy balance and get the actual enthalpy leaving the pump. So H2 real minus H1 is the work of the pump, which is 13.7, so we can calculate the actual enthalpy coming out is 431.3 kilojoules per kilogram. So Next thing we want to do is calculate the entropy change across the pump. This is a little bit complicated calculation. We calculate the delta work, the real work minus the ideal work, which calculating delta U is approximately for a liquid, is approximately the same thing as delta H. And delta U, or delta H for a liquid, is C heat capacity times dt. And recall CV is approximately equal to Cp for a liquid. So we'll use this change in enthalpy. This is the difference between the real and the ideal. That's the work that goes to friction, that excess work that goes to friction, which will end up increasing the temperature. And if we take that excess work and divide by the CCP or the CCV, we get 0.81. It would be the rise in temperature across the pump approximately. So ds then for a liquid, you recall, is CV or Cp dt over T. The integral of that is CV ln of T2 over T1. So I've calculated that, and our delta S across the pump is 0.0091. That'll be kilojoules per kilogram Kelvin. Now let's take a look at the turbine. For the turbine, we have state 3 coming in and state 4 coming out. The ideal work is the enthalpy in minus the ideal enthalpy out. And the ideal enthalpy out is a function of the exit pressure and the entering entropy, because we're saying that S3 is equal to S4 for the ideal pump. You can use the Moliere chart, or you can solve it using tables. Here, using tables, we find out that the quality of the ideal fluid leaving the pump, leaving the turbine, is 0.94. Go on from there to find the ideal enthalpy out is 2546. Could also be easily found using the Moliere chart, although you may not be as precise as this. Continuing with the turbine, we have the work ideal is Hn, H3 minus H4. Energy balance on the pump, H3 equals work per mass plus H4 if we take 1 pound as our basis. So our work ideally, I should put H4 ideal. Our ideal work is 1178 kilojoules per kilogram. So the work real in a turbine, the work when you're getting work, is always less than the ideal. So we'll multiply by, let's say, an 85% efficiency of the turbine. And this would be given to you in the problem statement. The efficiency of the turbine, in this case, 85%. So we find that we only get 1,000 kilojoules per kilogram of work from the pump. Again, plugging back into the energy balance gives us the real enthalpy out, which turns out to be, if we go in with 3724 and subtract off the turbine work, find that our enthalpy at state 4 is 2723 kilojoules per kilogram. Now, given the H, 2723, and the P, leaving the turbine, which is 1 bar, or 100 kPa, we'll find that the enthalpy leaving, using your knowledge of properties, is 7.4822 kilojoules per kilogram Kelvin. And using also T4 as a function of P4 and H4, find that T is equal to 123.2 degrees centigrade. Slightly superheated coming out of the turbine. Putting it all together, we can get a table of all our properties, and we can move forward from here and do our entropy balances and find the irreversibilities in all this equipment. You'll notice that as I go through the pump, which we've assumed to be adiabatic, the entropy is increasing, and that's due to friction. So this, let's see, this is greater than, leaving the entropy is always greater as you leave the equipment, unless you draw off heat. If you draw off heat, you can draw off entropy with the heat. But here, in the turbine, the adiabatic pump and the adiabatic turbine, the exit entropy is greater than the inlet entropy. So let's say for a basis of 1 kilogram, we can do our energy balances and find the work of the pump, which we've done before, 13.8 kilojoules per kilogram. The heat added, energy balance about the boiler superheater, allows you to calculate QH. The work of the turbine we had calculated, but the energy balance will bear that out, is 1001. And the heat loss to the cooling water is 2306 kilojoules per kilogram. We can now find the thermal efficiency of the plant, which is the net work divided by the heat added. Here I have work net over QH, or if we use a lowercase w, that's work per kilogram, WT minus WP per kilogram over QH. Again, everything per kilogram. Find that our thermal efficiency is only 30%. So we haven't really optimized this plant. It's not the most productive plant in the world, but here we have our thermal efficiency of 30%. If we compare this to the Carnot efficiency, and suppose we had the heat engine with, again, the heat input at 800 degrees centigrade, and the surroundings at 25 degrees centigrade, then we can take the Carnot efficiency, 1 minus TL over TH, is 72%. So we've got a long way to go in designing a plant that will try and approach this 72%, which is really limited by nature. This is limited by our imagination and our ability to design a plant. Oh, I guess I should say also economics really dictates how close to 72% we'd be able to get. In this case, with our current design, we're only getting 30%. Thermal efficiency, 30% of the heat that we put in goes to work. So we have 1 unit coming in, 0.3 units as work, and where's the rest go? 70% of the heat that we put in goes to the environment and heats up our streams and our ocean, our air. All right, now let's answer this question: how much cooling water do we need? So let's go back to the condenser and do an energy balance about the condenser. And our energy balance is mass of the steam. Here we have steam times H4 minus H1. The drop in energy of the steam is equal to the rise in energy of the cooling water. And if we take the steam to be a basis of 1 kilogram, then we'll find that the cooling water flow per kilogram needs to be 54.9. So that's a lot of cooling water. Steam going from in this cycle is changing phase, and there's a lot of energy tied up with changing phase. The cooling water is only changing temperature by about 10 degrees C. And by the way, that's typical of what's allowed by environmental regulations. You cannot heat up the cooling water too much because it'll damage the environment to put too hot of a cooling water out into the environment. So with the only 10 degrees rise in temperature of the cooling water, we need 54.9 kilograms cooling water for every kilogram of steam. Now we can do some entropy balances and calculate the irreversibilities around this unit. And this is nice to have an accounting of what happened to the potential that we had to produce power. We have that 70% Carnot efficiency and only 30% for our plant. So what happens to it? Here the entropy generated, if you do a balance about the condenser, it's mass of the steam times S out minus S in for the steam, plus mass of the cooling water times S out minus S in is equal to the entropy generated, comes out to 1.43 kilojoules per kilogram. In the pump, you recall our delta S, which is also the entropy generated, out minus N, is 0.0091. Very small compared to the condenser. And now let's look at the boiler. For the boiler, we have S out minus S in minus Q over T that was coming in. Q in over T in would be entropy generated for the boiler. And I have to be careful, make sure that's in degrees Kelvin here, absolute temperature. And that comes out to 2.63 kilojoules per kilogram. Whole lot of entropy generated in the boiler, and that's not unusual. There's a lot of driving force there. A lot of high gradients in your boiler produces a lot of entropy. In your turbine, we see in our turbine where the efficiency of the turbine compared to isentropic behavior was 85%, we're naturally going to have some entropy generated there, and that comes out to 0.46. So a summary of this would be, here's the Q, or the load, let's say the energy load of each of these units, the entropy generated, and the irreversibility for each of these units. And the irreversibility is based on a surrounding temperature of 298 K. So you call irreversibility as S generated times T of the surroundings. We took T of the surroundings to be 298 K. So I've calculated these numbers, and we've got all these irreversibilities. If you recall, that's the lost potential to produce power. And you see it's fairly high in the boiler and high in the condenser. When we add up all the units, we have 1,353 kilojoules per kilogram of steam of irreversibilities, or dissipation, or lost potential to produce work. What if the same QH were used in a Carnot engine? Take our same QH, the 3293 kilojoules per kilogram, and we would have produced 2,378 kilojoules of power. Now let's look at the work net that we actually got. That was the 1,001 out of the turbine minus the 13.8 used to run the pump. We got 987. What's the difference? In a Carnot engine, we would have gotten 2378 from this heat. In our actual engine, we got 987 kilojoules. The difference from that, the work that we might have gotten minus the work that we actually got, was the 1391 was the work lost. So 1391 is the difference from what we might have gotten with perfect engine Carnot to what we actually got. So now we have to look at most of the unconverted potential work. This 1391 is accounted for by our irreversibilities. We calculate that to be 1353, but the difference there's still some left unaccounted for. And so let's suppose we want to find out where it is. And where is it? Where's that remainder of 38 kilojoules? Well, I'll tell you, it's in that cooling water. Because you recall, anytime you have something with the potential above the surroundings, or even below the surroundings potential, then you have the ability to produce work from it. So we still have some moderately warm, or mildly warm, I should say, cooling water. We could put that through some ideal device. I'm going to call this a reversible device that would produce work while exchanging heat with the surroundings at 298 K. Produce this work, and let's see how much work we could get. Now the Q that we put into the condenser was 2268. If we brought that cooling water back down to its low temperature, and when we do the entropy balance and the energy balance on this reversible device, and I'd encourage you to do this, you find actually that Q, this is Q to the surroundings from this idealized reversible device, and the work that we could possibly produce, this is the maximum work we could produce out of any cycle, comes out to 38. Now that's just beautiful, because that's exactly the difference between the unconverted work from the ideal process compared to the real process, and the irreversibilities from all of those units that we've counted for. So where is that lost work? It's in the dissipation, which we have in irreversibilities, and it's also in the remaining potential in this process, which is our cooling water that's warmer than the surroundings. Remaining potentials. Okay, there it is in the cooling water at 35 degrees C. So now let's look at scale up of this plant, and we took a basis of 1 kilogram steam and produced 987 kilojoules per kilogram out of it. We need a net power from this plant of 150 megawatts, or 150,000 kilowatts, so we need to calculate how much steam we need to feed through there. Well, the work per time is the work per mass times the mass per time, m dot. Solve for m dot, it's 152 kilograms per second. That's a lot of steam, but this is a fairly good sized plant. So now let's scale the remaining flows. The QH, multiply the heat per mass times the mass per time. Turns out we need 500,000 kilowatts of heat added. That's what you're paying for when you run the plant. And the mass of the cooling water is 8,345 kilograms per second. I would encourage you, just for fun, to find out the volume flow of that in gallons per minute, and I think you'll be surprised how large that stream is. That's a lot of water, cooling water. It's a river, and many power plants will have a virtual river coming into them and out of the plant, in as cool water, out as warmer water. So let's see, there it is. Actually, I've done this for you. 132,000 gallons per minute. If you think of a swimming pool, a backyard swimming pool, as being about 30,000 gallons, you could fill one of those up in about 15 seconds there. Okay, the Rankine calculations we looked at. We completed the property chart. We did some pump calculations, turbine calculations, and of course the analysis depends on the problem statement. We did an irreversibility analysis. We computed the irreversibilities. We computed the difference between the ideal work we might have gotten from the Carnot cycle versus the real cycle, the Rankine cycle. And we asked if the irreversibilities explained the difference. In this case, there was a difference of 38, and that was accounted for by the potential left in the cooling water. If we go to scale up, we looked at the energy and entropy balances based on 1 kilogram of steam, and then used the given load, the 150 megawatts, to find the mass flow, and scaled all the remaining flows according to that. And so for homework, what I'd like you to do is look at Chapter 10, problems 21, 22, and 23, and then go through and do this irreversibility analysis for problem 23, assuming that heat enters at 600 C and that the environment is at 800. And that's kind of a nice summary of the Rankine cycle, and sort of a good overview of what happens to all our potential to do work that we started with there, with the heat coming in at 800 degrees C. So it takes care of quite a few things here.